agree to be recorded here. All right. Yeah, so welcome back. This is lecture 2 of Entanglement Dynamics. And just remind you, so, we're talking about the essentially growth of entanglement and the way systems come to thermal equilibrium effectively, even without the presence of a heat bath, as long as you have quantum chaos. That was kind of the pretext of the first lecture. So what we're going to do today is talk about some more generalities around this behavior, the kinds of models where you can see it, and some of the techniques we can use to probe it. And most of the time will then be spent talking about a particular solvable model where we can see this behavior explicitly and understand quite a lot about it, including deriving a sort of effective field theory or an effective equation of motion which describes the physics. And there's more references on the wiki, but I put a few of the key ones here. So this first paper, Entanglement Tsunami, is one of the first works in the context of ADS-CFT, which studied in detail this problem of entanglement growth. And then I will discuss in some detail the ideas in this entanglement and random circuits paper here, and also a little bit this time and probably more next time, this coarse-grained entanglement dynamics paper. Okay, and I put the references there, and they're also in the wiki along with the first lecture. Okay, so let's get going. Let's start out with a recap. So last time we reviewed something you would have seen in Patrick's lecture, but we reviewed the idea of entanglement. We talked about Rényi entropies, which are measures of entanglement, at least when the total state is pure. And we talked about dynamics of entanglement, broadly speaking, including the idea of bounds on entanglement growth. Okay. And then in the context of a 1D, what I call the quantum chaotic spin chain, so just a chain of spin halves or chain of qubits, we saw, first of all, that entanglement, as measured, for example, by the von Neumann entropy, grew linearly with time. And then it eventually saturated. And it saturated at a value which was related to the thermal entropy at the same energy density. For the graph I showed you, this was all the middle of the spectrum. So it corresponded to infinite temperature. The reason why that is because the entropy as a function of energy is maximized there. So if you remember your thermodynamics, the formula for temperature, if the entropy is at a max, then the temperature is infinity, or equivalently beta is 0. That, of course, doesn't happen typically in a quantum field theory, but in a spin chain where we have a bounded Hilbert space, it makes perfect sense. Okay. So I just showed you one example of that, but what I sort of intimated, and I'll claim explicitly here, this is a very general phenomenon. So very broad class of systems, spin chains, quantum field theories, holographic quantum field theories, random circuits, Clifford dynamics, all kinds of different sorts of systems have this same kind of behavior at this very high level, coarse level of description. Okay. So this is a very general phenomenon, this phenomenon of entanglement growth and thermalization. And again, the goal here is to understand at least the simplest model or way of thinking about this phenomenon and how it connects to other aspects of quantum dynamics. Okay, so let's talk now about models and methods. So I made a pretty big claim there. How do we know, why do we think that claim is true? So one class of models are what I'll just call finite size models. So the kind of thing you should have in mind here is like the spin chain I showed you last time where you had 14 qubits. So that was a 2 to the 14 dimensional Hilbert space, which is, a relatively big number, but easily manageable on a modern computer. And one of the main tools, perhaps the main tool for studying such systems is called exact diagonalization. And what that essentially means is that we just represent the wave function as a numerically exact vector in our computer. And we represent the Hamiltonian as a numerically exact matrix, just a big matrix. It's a very sparse matrix typically, and we can take advantage of the sparsity, but nevertheless, it's there. And this tool lets us essentially study the exact properties of this quantum mechanical model for any time, for any ring entropy, whatever you'd like to calculate up to numerical precision. Okay. So in particular, you could access any S alpha, which is quite nice. Other methods don't typically allow you to do this. So a lot of our intuition about von Neumann entropy in particular comes from these finite size models, because it's quite hard to access this in most other situations. One key limitation is from finite size effect. So in other words, we can do 14 spins. Maybe, if you're really using state-of-the-art machinery and you're working at the, level of the detailed specific hardware architecture, maybe you can do 30, 40, maybe 50 spins if you do it in a very, very clever way. But beyond that, it's essentially impossible. There's an exponential blow up of cost, and you just can't do any better than that on a classical machine. So there's really a pretty hard wall. And so, if there's some phenomenon that you want to see that is going to require more than 30, 40, 50 sites, this is not going to be a technique that will enable you to see that phenomenon. So in particular, because you would expect at low temperatures to have long mean free paths if you have a scattering of particles picture, or a long correlation length, that kind of physics is often hard to access using exact diagonalization, because you need like a lot of sites which are sort of doing nothing to make up this dilute set of low energy degrees of freedom. But nevertheless, it's very useful in part because it can access any ring entropy. So it really tells us a lot about that. Now we can also do large 1D systems. Here, a key tool is provided by tensor networks. So you're hearing about these in a different context from Michael. I don't know if he'll say anything about tensor network dynamics. But this is, in addition to providing toy models of entanglement and toy models of ADS-50, as you're going to hear about, it's an extremely powerful computational technology that allows us to say quite a lot about 1D. But there's a limitation, again, limited to relatively short time for exact results. And actually, the reason why this is exactly what we've been seeing here, which is that these tensor network methods require essentially low entanglement in the quantum state to work. And what we've seen is entanglement is growing. Okay, so as the entanglement grows, the resources you need to compute your tensor network accurately grow rapidly, in fact, exponentially with time. And this is why you can only go to certain fixed time. You can do a large system, which is nice and interesting, but you can only go to a certain fixed time for a given what's called bond dimension. So this can also be very useful, and you can try to do some approximate calculations, which can give you more insight, and that's very interesting. But I want to also especially mention, as a third case, the case of solvable models. And here, what I have in mind include what we'll talk about today, random circuits. The idea here is you have some random dynamics. So the dynamics is chosen randomly in each different element of an ensemble. And averaging over that randomness gives you power. It gives you a handle on the calculation, as we'll see. They're also what I'll call large N models. I'm not really going to explain what these are because I'm not going to use them, at least not right now. But feel free to ask on the Slack or during the lecture today if you want to know more. And in particular, ADS-CFT, which is a special kind of large N model, and many others, I would say these random circuits and ADS-CFT have really both had an outsized influence on our thinking about entanglement. In part because ADS-CFT is one place where you can actually compute the binomial entropy, at least in a certain large N limit, which is something you just often can't do any other way. Okay. And in this context, the sort of one of the key tools is the replica trick. In which case you're computing quantities like trace rho to the alpha for alpha an integer, and then trying to analytically continue. And the phrase that goes along with this is usually something called Carlson's theorem. I won't talk about this in detail. I'm happy to dig into it if you like during questions. But basically, this theorem says that if you have an analytic function, which trace rho to the alpha is in the half plane of real alpha greater than 0, if you have an analytic function and it satisfies certain growth bounds at infinity, doesn't grow too fast, then if you know it on a discrete set of points, say 1, say 2, 3, 4, up to infinity, then you know it exactly. Or said differently, if two functions agree on this set of points, say from 2 to infinity, then they have to be the same, right? Provided they're both analytic and have these growth bounds. But as we saw from the Renyi entropy example in the first lecture, this can be a little bit subtle in principle, because you really need to know it exactly in some sense. And you can have analytic functions that almost agree, but then are very different elsewhere. Although, as I sort of suggested in experience, based on my experience in practice, this is sort of rarely an issue, although I did post in the Slack one interesting case where the entanglement entropy grows linearly with time, but the Renyi entropy goes like the square root of time. And it's rooted in these kind of subtleties about the fact that Renyi entropies are really probing in principle different physics.
Excuse me?
Yes.
How do you know that it's an analytic function when it's something so ill-defined like the trace of a density matrix in a quantum field theory?
Good. Yeah, I should be a little careful. So certainly it's analytic when it's a finite system, which is what I mainly have in mind here.
Okay.
And using ideas of compression that Patrick, I think, talked about in his lectures last week, you can try to argue on fairly general grounds that you can compress even an infinite dimensional Hilbert space to a finite one. But I would say also in quantum field theory, there's a lot of additional structure that can help you make sense of this. And still be confident that you have some analytic structure. Of course, this quantity itself is not even well defined, so it's not analytic. But there are like alpha, like the relative entropy and alpha versions of that can make sense and can have nice analytic properties. Okay, and then you can still get what you want out. That's a good question. Other questions? So I would say it's sort of these finite size models which is a nice playground, to some extent, the tensor network methods, and then especially random circuits and ADS-CFT that are kind of the strongest evidence we have for the picture I'm going to present in the rest of this talk. Okay, so let me, before I go on to the details of random circuits as an example, let me just say why I care. There's a couple of reasons. The first is kind of what I'd say is a basic science reason. I mean, this fact that there exists this broad class of systems that we can call quantum chaotic, which have the property that they come to thermal equilibrium, that's very interesting. And it's a very generic property of a large class of physical systems. It has to do with all kinds of deep issues, like under what conditions statistical mechanics makes sense, what conditions it works in an isolated system, etc. And so certainly I'm just interested in, understanding deeply the problem of, when and how isolated systems come to an effective equilibrium. And as I said, the dynamics of entanglement is very natural, because one of the key questions you have to ask is sort of, where does the entropy come from? What is playing the role of entropy, of thermal entropy in your system? And entanglement actually is what plays that role. Okay, so it's a basic question. Another reason why I personally care is that entanglement dynamics is closely related to space-time dynamics. This is sharpest in the context of ADS-CFT, which you'll hear about. I'm not sure how far Netta got yesterday and today, but you'll certainly hear a lot about this, I imagine. And also to the black hole information problem, which you're going to hear more about as well. In particular, because entanglement in gravity and Einstein gravity is related directly to the geometry of space-time. Changes in entanglement are related to changes in the geometry of space-time. And so things like gravitational waves and infalling matter into a black hole all leaves an imprint on entanglement. That's quite interesting. And the final thing is I'll mention, again, personally why I care is that this subject is a key input into approximate methods. To describe quantum dynamics. So for example, I talked about tensor networks and how if you want an exact result, that is limited to short time. But if you're interested in something approximate, or if you want to understand how an effectively coarse-grained thermal-like state emerges, perhaps you can do more if you understand enough about the entanglement structure. And this has actually a very long and profitable history, something that we're still thinking about today. And the stakes here are really, there's a lot to be gained, because, for example, one of the things we care a great deal about in a variety of contexts is, for example, how energy and conserved quantities are transported by the system. We know at long wavelengths is described by hydrodynamics, but the basic parameters that enter that effective field theory, like the diffusion constant, the viscosity, etc., are not known typically. And computing them is a hard problem, where you need to cross over from the quantum dynamics to this effective classical description. That's a very hard problem we don't know how to solve. But this kind of data is ubiquitous from the quark-gluon plasma experiments at RIC and elsewhere to all kinds of measurements of transport and strongly interacting quantum many-body systems, solid-state systems, atomic molecular optical systems. This is wealth of data that we just don't understand, basically, because we don't have a machine. We don't have a way of thinking about how to go from microscopic to the macroscopic. And this kind of entanglement dynamic story actually has offered a lot of insight into how this works and help us design interesting techniques that might be able to approximately bridge this gap and, therefore give us a lot more computational power. So are there any questions about these motivations or about the models? I'll pause here and give folks a chance to jump in. Okay. So let's then move on to the basic intuition. Okay, so let me draw a little cartoon of the dynamics. These are qubits or spins. Time is moving up. And these qubits, they interact via two-body interactions. So each of these blocks represents a unitary which acts on the indicated qubits on its edges. There can be other additional parts of the system, etc. And we can consider different moments in time. So this is t equals 0. This is t equals 1, t equals 2, etc. And at t equals 1, there's no entanglement. That's what this initial dots at the bottom here are supposed to indicate. It's an unentangled initial state. These dots down here. And then as I apply unitary transformations, I can generate some entanglements. We don't know exactly how much entanglement gets generated, but I can generate some. And what you can see is that if you say, look at this cut here, and call that A and call that B, then initially A and B are unentangled. And going from time 0 to 1, you are going to generate some entanglement because of this unitary transformation, which couples them. Then in going from 1 to 2, there's no unitary that connects them, right? You only have unitaries within A and within B. And so we know from what we said about the general facts about unitary invariance that entanglement won't change, right? But then I go to step 2 to 3, and again, I have this unitary which connects them. So the basic point here is that you kind of imagine this stack of unitaries going up. What's your basic expectation? Well, the entanglement is going to grow a little bit every couple of steps, right? And that at a coarse grain level would be a linear growth of entanglement, linear with time, which is what we saw in our exact calculation. And then eventually, if this linear growth continues forever, it'll have to saturate if A is a finite size region, because the entropy of A can never be bigger than the log of the dimension of A. So this basic intuition already sort of roughly captured what you saw in the spin chain data. We had a period of linear growth, some kind of crossover to a saturated region. From another point of view, we can think about dynamics, H, which is dynamics on A, dynamics on B, plus some dynamics which couples them. So it looks like this. This is A, this is B. And there's this single term, actually. If you look at the Hamiltonian that I wrote, there was a single term in the Hamiltonian that coupled A and B. Right, it was the ZZ term between the rightmost spin in A and the leftmost spin in B. So just this one term, which was responsible for the entanglement growth. Of course, the growth was not just proportional to, it's related to the quantity J, which was set the scale of that term, the energy scale. But we saw from the Ancilla assisted discussion that, of course, the growth rate can depend on what's in A and B as well. They don't explicitly cause the growth, but they influence the effective rate of growth due to this coupling. And so again, if you look at your bound that we just talked about, the small incremental entangling theorem, this says that the entropy of A, since it's coupled by just this single term, can be no more than some constant times J. because the norm of this Hamiltonian is bounded. There's just some constant out in front, and J is the energy scale. Right? So again, this would say if you have some more or less generic behavior, well, you certainly can't have more than a constant growth rate. And so, okay, you would expect that maybe not saturating the bound, but growing at the same kind of characteristic rate as allowed by the bound. So again, you would expect linear growth and then eventually saturation. So this is just to really drill into you that this linear growth is what you should expect, at least in 1D. There's a simple picture for it, and it's absolutely, the most naive possible thing, and it's what you see in this next. Now let's be a little bit more quantitative. So let me draw a line with open boundary conditions of length L. And let me consider an interval from 0 to x, right? And I'll call that AX. And let's suppose that t equals 0 again, that the entropy, which is just defined to be the entropy of A of x, but this is equal to 0, right? So it's initially unentangled state. Now, as t goes to infinity, what do we expect? Well, if we're going to have some kind of equilibrium state, then what we would have is some equilibrium entropy density, which I'll write SEQ. That's the equilibrium entropy per site. And you'd be tempted to say that it's x, it just grows linearly with size, because that's what would happen in thermal equilibrium. But the total state is still pure by hypothesis. And we have to have this property that the entropy of AX and the entropy of its complement are the same. So it can't just be linear in x, it has to cross over once x is half the system size, because then the entropy should go back down again. So what you actually get is the minimum of x and L minus x. So in other words, the entropy agrees with its thermal-like value up until approximately half the system size. And then once you go more than half the system size, entropy has to go down again, right? Because the entropy of this other region, AX bar, which is the complement, we have to have that the entropy of AX is the entropy of AX bar, because it's a pure state. And this factor here just accounts for that. So this is a phenomenological, and just a guess, which says, let's take the thermal equilibrium value of entropy and make it compatible with a pure state. And in particular, this thing obeys this Sx infinity is equal to SL minus x infinity, which is the purity constraint. Okay, so based on what we said before, now we can put forward a hypothesis. Or a simple effective model, which says that let's imagine that the rate of change of entanglement is proportional to this equilibrium value, which sets the magnitude, times a rate, which I'll call gamma. And this rate can in principle depend on the spatial gradient of this quantity. Right. This is a little bit funny. It's not like there's a local quantity that's varying. It's like I'm adding more to the region. And I'm asking how the entropy changes as I add more to the region. Right.
Could you give a little more intuition for that last, like, why should this be proportional to something that depends on the entropy gradient?
Yeah, that's what I was about to do, but that's a great question. So let's discuss this. Why is this reasonable? Well, we know that in equilibrium, S of x equals SEQ min XL minus X. And so in particular, the derivative of S is SEQ up to a plus or minus. Right. And since we want the equilibrium configuration to be stable, it had better be the case that gamma of SEQ is equal to 0. So this is like stability of equilibrium. So what it's saying is that basically in equilibrium you have an entanglement gradient. And since you want equilibrium to be a fixed point, you have to make sure that the rate vanishes when that gradient is present. Now in the initial state, you also have some entanglement, or you also have no entanglement. So in the initial state, you have no entanglement and no gradient. And there you have entanglement growth, right? So in other words, the growth rate seems to depend, at least in these two extreme cases, where there's either no gradient or the biggest possible gradient. It depends on the gradient. And so it's natural to guess that maybe it's a function of the gradient. Right? That is to say, the closer you are to equilibrium, so this is one point. And then another point is if we start in partial entangled state, for which S of x at t equals 0 is, say, some S naught, then we still expect entanglement growth. But now it's going to be at some rate, which in principle can depend on S naught. And so you can just go, you can go to the numerics that I showed you. Instead of putting in an initially unentangled state, you could put in a state with partial entanglement. And what you'll find is that the rate is indeed slower, right? So it's intuitively reasonable that basically as you take the gradient from 0 to the equilibrium value, the rate slows down, and it slows down in a smooth way. And that's why you have this this gradient dependent rate. And then we say, okay, we can add higher derivative terms in the spirit of effective field theory. That's all fine. But here we're trying to get the simplest possible, most minimal description we can have of the physics.
Is there something controlling this like higher derivative expansion like in hydrodynamics? Or like why can we truncate this?
That's a good question. And let's see, what can I say to that? I don't have a very simple answer to that. I mean, I think it's true that there's often something that controls it, but I can't think of a very satisfying general statement. But one thing that is true is that this dynamics does not generate the gradient. So if you start with 0 gradient as you have in an unentangled state, you don't make it, and at least not inside the region where for the values of x for which the entanglement's growing. So it's self-consistent to just drop all derivatives actually.
Thank you.
Mm-hmm. Yeah, I'll think more about that and get back to you later if I think of a better, interesting example. So yeah, I want to make this point explicit. This dynamics does not generate spatial gradient while growth is happening. This is because if you solve that, well, let me just write down the solution. So S of X and T becomes the minimum, let's say S equilibrium times the min of X, L minus X, and VET, where VE is defined to be gamma 0. This is for an unentangled initial state. So in particular, if the entropy is still dynamical, if it's changing with time, it's just given by VET. And we saw that on the plot, right? All the entropies lined up at first until they slowly peeled off and saturated. So you start with no gradient, and you actually don't make a gradient. You only make the gradient once you saturate it. So the gradient kind of emerges from the saturation, from the different size regions peeling off to their saturated value at different times. But in the regime, for values of X for which X and X plus 1 and X plus 2, or as a function of X, they're all still growing, then there's no gradient generated by this dynamics. Right. So what does it look like if I plot it out? I'm imagining there's sight, but that doesn't matter too much. That's the picture. And if you look back at our numerical plot, this is indeed a pretty reasonable, I would say. You know, it's a little bit up to the beholder how much you think this is like capturing the physics, but it gives you a reasonably good account of the qualitative features. That is, you have some kind of linear growth, the regions more or less coincide, and then they peel off and saturate at different times, depending on their size. I would say the things you're not capturing correctly are definitely the early time growth down here. But that's very model dependent, so you wouldn't necessarily expect some very general effective theory to capture that. And then the saturation, like the crossover between linear growth and the saturated value, is also not necessarily captured very well by this model. And that can be an interesting sort of late time regime of the dynamics, how you're approaching the totally equilibrated state.
Can I ask a question?
Please.
I'm just trying to understand the equation you wrote down with the plot. So are you like how is the system size here X coming into this plot? Is that what you're choosing as like the 1, 2, 3? This is your or like you said, the sites, excuse me.
Yeah, like that.
Okay, right. So the different curves is what
Different curves of different system sizes.
Okay. And the linear growth here is what's proportional to this VE, which I guess would be the entanglement velocity.
Correct. Yeah, the slope here is VE, which, yeah, I didn't say the words yet, but this is called the entanglement velocity.
Okay.
Yeah, great question.
Thank you.
And can you remind me, was gamma here just a linear interpolation between the two extreme values at 0 and S equilibrium?
No, I didn't say what it was. I just said there's some gamma,
okay.
and we expect, in principle, we expect it to depend on the model. So there's not a universal function here.
But so I don't understand then this plot that you just drew seems to me like it would strongly depend on the details of gamma.
Yeah, so the interesting thing, at least in 1D, is that it really doesn't actually. And the reason is that, at least, so if I look at it as a function of the initial entanglement value, this S naught, then you just probe the whole set of gammas. But in the case where I start from an unentangled initial state, then all that matters is gamma 0. And then you just have the saturation. And the reason why that's all that matters is that it does not generate a slope. If it did, then you have to go through the whole, it would depend on the whole thing. And in higher dimensions, that's what happens. Like if you have a, for example, if you have a strip region, then this picture still works. But if you have like a spherical region, then it turns out to depend on the whole curve gamma of S, right? So this is a bit of a special case.
Right, I guess because the smaller regions saturate earlier, the ds/dx for the larger regions is never going to change until after the point of saturation.
Yeah. And we'll see a little, hopefully by the very end of today, a very different picture which makes this much more explicit. A membrane picture, not to give away the conclusion. Any additional questions about this? So we have a toy model, and now I want to take this toy model, which is really a phenomenological model, and we want to study it in more detail or understand how it emerges from something microscopic and precise. So for that, I'm going to talk about a random circuit model. I should say, let's see, this hypothesis here, this is discussed most clearly, I would say, in the Jonet et al. Paper. And then here, this is the Nahum et al. That I talked about on the first slide. Okay, so here's the model. We have, again, a chain. Now we have Q states per site. So this is like a free parameter. And just like you can get control in a large N limit, you can also get control in a large Q limit. So this is another thing that we theorists like to do, take some artificial limits to give you some handle, and then hopefully that picture extends. And the reason why it's called a random circuit dynamics is we have the following rule. We select a bond, then we apply random unitary, and then we go back to 1. So the random unitary looks like this. U. And U is a Q by Q, Q squared by Q squared unitary, which I choose randomly from what's called the Haar measure on unitary. So it's just the measure which is uniform over the space of all unitaries. And I won't define that precisely, but you can easily look up on Wikipedia or wherever the properties of that thing. Okay, so it's very simple. You have a chain, you pick a bond at every step, you apply a random unitary, then you repeat. Picking a new bond, applying a unitary. And this is like one unitary at a time, but we can scale the rate so that effectively on average you're applying 1 unitary per bond per time step, right? So that's like an extensive dynamics.
Just a quick question.
Yeah, please.
So the bond doesn't have to be between nearest neighbors, right?
It does, it does.
Oh, it does? Okay.
Yeah, nearest neighbor bond. Thank you. So we can consider a more general class of models where you allow further range interactions or parallel interactions, and we've studied that. Many people have studied that, but here we're just considering nearest neighbor.
Okay.
Other questions? So in this model, you can study the following thing. You can study many things, but one thing you can look at is the dynamics of S naught. This is the max entropy or Hartley entropy. And in this model, you find the following incredibly simple rule for the dynamics of S naught. S naught at link x. So think about this as x, x minus 1, x plus 1. So we're just labeling things by the link instead of by the site. And as we increment time by one step, so we do one step of this procedure, if we look at the bond or we apply the unitary, then we find that this is equal to the minimum So in other words, you look at the bond to your left and the bond to your right. You ask how much entropy there is for all the sites to the left or all the sites to the left with that extra bond inserted. You ask which of those has the smallest max entropy, and you take that value and add log Q to it. Log Q is the largest possible value that you can increment for this Q state system. I just put it over here so it's clear it's not inside the min. And I can give you a simple picture of this. So what this rule implies.
Hey, Brian, one question.
Yeah, please.
Are you taking the minimum between x minus 1 and x plus 1 because you're still assuming that the state of the whole system is pure?
The state of the whole system is pure, that's true. And what enters is x minus 1 and x plus 1 because I'm assuming the bond is on x. So I'm looking at the particular bond where I'm applying the unitary, which I've chosen randomly. And at that particular bond, the effect of this unitary transformation with probability 1 over this random ensemble is to change the max entropy across that bond to the minimum of the left and right plus log Q. So the state is pure, but I'm not using like the global purity for this calculation.
Then I'm just not sure I understand where the minimum arises from in this case.
Well, let me say it this way. So, I mean, there's a calculation I didn't show, but let me give you some additional intuition. So one thing which is true is that x plus 1 t minus sx t is less than or equal to log Q. So for any pair of neighbors, in any neighboring set of bonds, this is always true at any time. You just add one more site, you can't change the max entropy by more than log Q. That's also true for the one-norm entropy. So all that rule says is that you change S naught of X on your bonds as big as that, you make it as big a change as possible consistent with this rule, right? And the derivation of that fact follows from just analyzing a random circuit, which I'll sketch for you in a second, but it's let's say I don't have a more simple explanation at this level of detail.
Thanks.
Well, let me draw this picture here. So this rule implies that it's S naught is always log Q times an integer. So we can think of that integer as like a height. And then we can make a picture like this. We have essentially a surface or a stack of boxes where I have an integer height, integer number of boxes in each stack. And the rule for dynamics looks like this. If I have this kind of stack, well, then the minimum, if this is the S naught of each of these x's, x plus 1, x minus 1, this would go to this configuration. So we would add one new box. We increase the entropy of that X by the minimum of the left and the right, which is both the black level, and we just add 1 in units of log Q to it. Similarly,
Can I ask a question really quick?
please.
Maybe I missed this. It, what you're doing now, is this your rule that you're imposing on the system, or is this something that you found by analyzing the system when you just apply a random unitary? I guess
Yeah.
I didn't understand that distinction.
Sorry, I wasn't clear. So this is the rule. This is the rule of dynamics. And this blue star rule follows from that microscopic rule. Okay. I did not show you the derivation, but it just follows as a math fact from that setup.
Okay, I see. Okay, thank you.
Yep.
And this is for a finite chain, not a periodic one.
No, this is all local, so I didn't say anything about boundary conditions really. But let's
Okay,
say we
and-
have open boundary conditions.
And is Sx the entropy at site X or at everything to the one side of site X?
Yeah, it's this picture I had before. So where can I write it? Entropy of sites left of X.
Okay, thanks.
So it's the same kind of regions we were considering
Yeah.
in the toy model before. Other questions? Okay, let me finish my pictures. And then the final picture I'll make is this one. And you get that. So what happens? So if you have a flat set of boxes, you add 1 box. If you have this corner here, you can add a box. If you have a hole, you can add 2 boxes. Again, it's just a pictorial representation of that rule. And if you have this growing staircase, you actually add no boxes. And that should immediately remind you of the linear pyramid-like shape we had for equilibrium. So this is saying that according to this rule, if you have linearly growing entropy, which is growing as rapidly as it can in space, then nothing happens to it. So that's an equilibrium configuration. So these are just a pictorial representation of that rule, the blue star rule, which I claim without proof follows from the microscopic model I wrote down.
Does this model need an infinitely long chain to make sense?
No.
What happens at the edges of the staircase then? Because at some point the staircase has to level out and turn around.
Yeah, so what you would get in a finite size chain, late time finite size open boundary conditions is a pyramid. Which is
Oh, I see. And I guess this is an equilibrium configuration because even the peak of the pyramid is fine.
It's just that it's this box version of the equilibrium state we had before. So that would be the late time value for this dynamics. Now, I'll claim also without proof that if you take the limit of very large Q, then this also applies to some degree of approximation, which you can control, to all of the Renyi entropies, not just to S naught. which means q to infinity with t fixed, applies to all reigning entropies, including the von Neumann entropy, up to corrections that vanish as q goes to infinity. And again, this is a technical result. I encourage you to look at the paper if you'd like the details, or ask me afterwards. It's really not so hard to prove. You just need to average over the unitary group, which is something that there exists technology to do. So it takes, I would say, you know, a couple of hours to familiarize yourself with the unitary group averaging technology. You don't need a particularly elaborate case of it here. And then using that technology, you can verify these two blue starred claims. Right. So I'm 100% confident you can all do it. I just don't want to go through the algebra of that here in front of you. Okay, so what's the punchline? This is equivalent to a model of random surface growth in the so-called Kardar, Parisi, Zhang universality class. This is always abbreviated KPZ. This is a super well-studied model written down in a totally different context, as I said, to describe surface growth. But it's a super well-studied model. It appears all over the place in all kinds of different areas of physics and math and otherwise. And once we make this identification, which is another contribution of this paper, then at once we get a nice continuum description. Looking at the dynamics of entanglement now, let's say the von Neumann entropy, which we allow it to do because of the second blue star. And we're going to, of course, have a continuum, so we're coarse graining this. We're not going to track the detail level, lattice scale level physics. But in the KPZ class, if you have this height variable, which is the entropy here, it has the following differential equation, which it satisfies. There's a gradient term, which is like a diffusive term. So the little blocks can diffuse along the surface. There's a famous nonlinear term, which has to do with, in the height description, with the fact that the surface is curved, then the rate of growth changes in an interesting way. Then there can be a constant growth rate, C. And there can be a stochastic, meaning random in space and time, uncorrelated white noise additional growth, eta of x. This is a white noise, which just means it's uncorrelated in space and uncorrelated in time. And this is the famous KPZ equation. And what we've learned is that in this particular model of dynamics, the growth of entanglement is described by the growth of a random surface that obeys this KPZ equation once we've coarse-grained and taken account of continuum limit. Again, I'm not proving this to you, but I'm making a claim which you can, well, this KPZ is a huge literature, but it's not hard to figure out how to solve it. You can look at the original paper in 1D. So let me start out by ignoring the noise. Then what do we get? We get dt of s new dx squared s minus lambda over 2 plus c. Now let's try a solution of the form s of x and t equals s naught x plus gamma t. That solved this equation. The second derivative of s is 0, so the first diffusive term is irrelevant. The first derivative is a constant, and so what we get is the gamma equals nu minus lambda over 2 s naught squared, sorry, no nu, plus c, which I can write as c times 1 minus So this is a key formula. What we're seeing is that exactly the kind of toy model we wrote down phenomenologically to describe entanglement growth is spit out by the effective description of this model. And moreover, we see that the rate gamma, the rate gamma depends, it has some normalization c, which sets the unit of time. It depends on the equilibrium, on the initial entanglement slope, that's S naught. It vanishes when S naught is equal to a value which I call S equilibrium that depends on the parameters of the KPZ equation. And it has some characteristic quadratic form. So it's C at S naught equals 0, and then it decreases and vanishes at S naught equals S equilibrium. So it's exactly giving us the broad strokes of our phenomenological description, and moreover gives a precise formula for gamma in this context.
Should this little toy solution, I mean, if S naught is a constant that doesn't depend on time, does this little toy solution, I guess it doesn't have the right long time behavior because it never saturates in entanglement. So what should we take it as teaching us?
That's right. Yeah, this is ignoring saturation. And that's because, let's say, how to say it, this equation by itself, without talking about the boundary conditions, in the context of height, it enjoys a symmetry, which is that the height can go to height plus a constant. So the surface can grow just as well from here or from there. Now that's not really a symmetry of the microscopic quantum problem. In particular, if I have a pinning at the edges because I require that the entropy vanish when I have no sites or all the sites, that imposes a constraint. So this solution will fail to agree with the boundary condition near the two ends, and that will introduce the saturation effect, which you can then solve this through in a more general setup and recover some smoothed out version of the phenomenological formula we had. Other questions? Okay, so I'll just also mention that with noise, the dominant effect is still linear growth. But there are subleading terms. In fact, what happens in this case is that S of x and t averaged over noise, the noise eta, which we think of as the physical entropy, has a constant term and then another term which goes like t to the 1/3. And this 1/3 is a critical exponent that comes out of the solution of this KPZ equation in 1D. So this model is exactly solvable in 1D, and you get this 1/3. You can get a rough sense for this as follows. If you go back to our equation, let me just copy it. If you just thought about things as being flat and you consider this as like a white noise, then you might think, first of all, that it's sort of like a Brownian walk, Brownian motion. For a random walk, you expect square root of time scaling. That's the typical size of the fluctuation, and it's not biased one way or the other. So the net growth in one direction leaves a bias, and the fact that you have these terms here which force the surface to want to be uniform slow down that square root of t growth a little bit and give you this t to the 1/3. But you shouldn't be surprised that it's subleading to the overall linear growth, because even if it was an unfettered random walk, it would only typically grow like square root of t. So there's beautiful statistical physics here. You can solve this and study it to death, and it's great fun. And here we've shown that it appears to describe this particular entanglement dynamics of this random circuit model. And then the hope would be, okay, we have this one solvable model where we can work things out in detail. Maybe this provides an effective theory that applies more broadly. However, this KPZ surface growth way of thinking about things turns out not to be the most efficient way of generalizing. To explain the more efficient way of generalizing, I'm going to turn to the last subject for today, which I'll discuss very briefly and then pick up next time, which is the minimal cut picture. And the idea of that picture is as follows. Let me get my... Let's go back to our circuit. The idea of the minimal cut picture is that we can get a bound on entanglement by looking for the minimal number of bonds or links that must be cut to isolate AX. So here again, this region here up to X, this is A of X. And so the idea of this prescription is that I look in this network, which is a picture as a function of time of all my random unitaries laid down according to my random rules. And I go to this network and I start from the end of A of X here. And I look at cuts that cut through the different lines. So this is a cut that cuts through 1, 2, 3, 4, 5 links or bonds. And I can say on totally general grounds that the entropy of A of X is less than 5 times log Q in this model. That's the minimal cut formula. You'll see a lot more about this in Michael's lectures, I'm sure. Tensor networks. This is essentially a tensor network formula. And so you can get the best bound by taking the minimal cut. In this case, it would correspond to the following curve.
Brian, you have 5 minutes.
Okay, great. Let me choose pink. that curve cuts two bonds here and there, and then in this case, I think is the best bound you can get. And so this is another way of bounding the entanglement. But again, in this very nice random circuit model, this bound in the random circuit model this bound is tight. And we have a description in terms of what's called a directed polymer in a random environment. So this minimal curve is the polymer, and the random environment is the set of these blue boxes it has to sort of dodge around or try to minimize itself in. So just like it's like a polymer that's in some random potential landscape. And it's known that that statistical mechanics problem in 1D is again equivalent to KPZ. Right? It's in the same universality class. So at this level of thinking, this is just another formulation of another exact formulation of the entanglement dynamics at large Q in this random circuit model. It's manifestly, well, not manifestly, but it's known to be in the same universality class as KPZ, so it's giving all of the same universal answers. But this picture turns out to be more generalizable. And it leads us to a theory of an entanglement membrane or curve in 1D. An effective theory of entanglement membrane, which is something that at least makes sense more broadly, and you can then conjecture gives the generic behavior for chaotic quantum many-body systems in a variety of dimensions, etc. And so what you can expect next time is we'll discuss this membrane theory in detail. We'll see how it relates to the phenomenological gamma quantity we defined in our phenomenological model, and we saw an example of the random circuit case. We'll see how essentially the tension of this membrane is related to that quantity. And we'll see how it predicts all kinds of interesting formulas and relations for entanglement growth, operator dynamics, etc., in these chaotic systems for which it applies. And I'll also tell you a little bit about what kinds of theories it is known to apply in. One of the key examples besides this random circuit case is ADS-CFT. So Mark Mazet wrote a very nice paper a couple of years ago where he pointed out that the Ryuta-Hinagi formula, which you will either learn about soon or have already heard about, actually implies this membrane picture with a calculable value of the tension and a calculable version of that quantity gamma. Okay. So we'll talk a little bit about that next time. So next time will be this effective theory, and then the final meeting will be using that effective theory in a novel context, this measurement-induced phase transition for the final lecture. All right, thanks.
Great, thank you. All right, questions for Brian? I guess nobody has.
Just to clarify something.
Okay.
From your previous picture of the cut.
Yeah.
Do you need to separate, say, region A from the complement for all times, or like where does it need to end for the bottom of the picture?
Yeah, good question. So this is for an unentangled initial state. So in effect, there's no cost for where you end here on the bottom. If there was entanglement down here, you had to put that cost in there. And so you'd have the cost of the bonds cut, as well as the cost of where it hits the bottom, which is some initial amount of entanglement. And that would be the more general minimization quantity. So we'll see that in some detail next time. But yeah, it's a good question.
Okay, thanks.
Anyone else?
Can I ask a question?
Please.
So when you were discussing the KPZ model, you said that this is we are looking at effective field theory description of this discrete model. So by that, do you mean you take the lattice size to 0, and then you're still looking at a quantum theory, but you're just taking the lattice size to 0, and that, but you are transporting the problem to a different problem which has the same equation, and then you're solving that equation, and that helps you to actually understand the continuum limit?
I would say it means the following. I have this underlying microscopic quantum system, and I have this rule for entanglement dynamics of that system, which is a discrete rule. And what this continuum description does is it's another model that doesn't have the same microscopic description, but which gives the same universal quantities. So for example, this T and this T to the 1/3, those precise powers. Hold on, I'm gonna let the slides catch up. Yeah, this power T to the 1, this power T to the 1/3, that's the same in both models. So the discrete microscopic model also has a T and a T to the 1/3. These coefficients number and number prime can depend on microscopic details. So they may differ depending on how you regulate that KPZ model. But that's a sense of universality here. So we're not explicitly taking the lattice spacing to 0. We're just having an effective long wavelength description where you have two different, say, UV completions with the same infrared description up to irrelevant operators. So that's the spirit that we're using here.
Okay, so can I say at least that the size of your system is very big compared to the individual lattice distance?
Correct, yeah.
Okay.
Anything else?
Can I ask about that cut surface?
Yeah.
So can I understand that as kind of what we said before, that really the entanglement can only change by a certain amount, by the log of the rank of the bond, I think is what it was. And you're only looking at the boundary of the region, so you just need to make those cuts to say, okay, it can only grow by this much.
Precisely, that's exactly right.
Okay, and then I have another question, which is, it draws out this nice line in time, right? And I was curious if this is in some way related to like the area terms that come up, because this is it's an area in space-time, but maybe not so much in X, right? You kind of see what I'm saying? Like it almost looks like you're tracing out an area through time. Right?
Yeah, I think that's actually the right picture. Like in ADS-CFT, that's explicitly what happens.
Right.
And more generally here, what's going on is sort of you have entanglement can only be generated at the edge because that's the thing which couples the two sides. So it's kind of like the trajectory of this edge in time, like how it works on the system as a function of time, very roughly speaking. That's at least the intuition I have.
Okay. All right. Thank you.
Yep. Actually, on that, just a follow-up, there is no notion of this thing being space-like or time-like, right? Or is there?
There actually will be, well, okay, but that's probably too much. Let me say there will be a notion of maximum speed.
Okay.
And we'll see that next time. And that has to do with the fact that this circuit has an effective light cone, and it won't spread information faster than that speed. So actually, we'll see that next time, that there is a notion of maximum speed.
Good.
That was actually something else that I was wondering about too.
Yeah,
Okay.
great question, and we'll see it next time.
Great. Any other questions? Okay, I guess we can end the recording part.